Welcome to this problem walkthrough. Today, we'll be exploring problem number 1458, titled Max. Product of two subsequences. This is an intriguing problem that combines elements of dynamic programming and optimization. Let's dive in and break it down step by step. In this problem, we are tasked with finding the maximum dot product between two subsequences of two given integer arrays, nums1 and nums2. Now, a subsequence is simply a sequence derived from an array by deleting some or no elements, but crucially, without changing the order of the remaining elements. For instance, 2, 3, 5 is a valid subsequence of 1, 2, 3, 4, 5, but 1, 5 is not, because the relative order is disrupted. The dot product itself is defined as the sum of the products of corresponding elements in two arrays of the same length. So, if we have arrays A and B, the dot product would be calculated as A, 0, B, 0, plus A, 1, B, 1, and so on, up to their last elements. Let's look at some examples to make this clearer. In the first example, we have nums1 as 2, 1, minus 2, 5, and nums2 as 3, 0, minus 6. The maximum dot product here is 18. This is achieved by taking the subsequence 2, 5 from nums1 and 3, minus 6 from nums2. Calculating the dot product gives us 2 3 plus 5 minus 6, which equals 6, 30, and that results in 18. In the second example, nums1 is 3, minus 2, and nums2 is 2, minus 6, 7. The maximum dot product here is 21, which comes from selecting the subsequences 3 from nums1 and 7 from nums2. The calculation here is straightforward, 3 7 equals 21. In the third example, nums1 is -1, minus 1, and nums2 is 1, 1. The maximum dot product in this case is -1. This is achieved by taking the subsequences -1 from nums1 and 1 from nums2. When we calculate the dot product, it's simply -1 1, which gives -1. Now, let's consider the constraints of the problem. Both arrays can have lengths between 1 and 500, and the values within the arrays can range from -1000 to 1000. These constraints mean the solution needs to be efficient enough to handle larger inputs. Additionally, handling negative numbers is crucial in this problem, as the optimal subsequence might involve products of negative values yielding positive results. There are a few key edge cases to consider. First, when all elements in one or both arrays are negative, the algorithm should ensure that it finds the combination of two negative numbers that maximize the dot product. For example, if nums1 is -3, minus 2, and nums2 is -5, minus 7, the best result might come from multiplying two negatives to produce a positive. Next, the arrays can have different lengths, so the solution cannot assume they are the same size and must work with subsequences of varying lengths. Also, when dealing with single-element arrays, like nums1 equals -1 and nums2 equals 2, the dot product is simply the product of those two numbers. Lastly, if one of the arrays contains zeros, such as nums1 equals 0, 0, 0, and nums2 equals 5, minus 3, 2, the algorithm must account for zeros appropriately, ensuring the result is still maximized despite the presence of neutral elements. When tackling the problem of finding the maximum dot product of two subsequences, we first consider the brute force approach. The intuition here is straightforward: generate all possible subsequences of nums1 and nums2, calculate the dot product for each pair of subsequences, and then find the maximum value. A subsequence retains the relative order of elements, but the sheer number of possible subsequences, 2 n plus m, where n and m are the lengths of the arrays, makes this method computationally infeasible. For arrays of size up to 500, as allowed by the problem constraints, this approach would take an exponential amount of time, making it impractical. Instead, we turn to dynamic programming as an optimized solution. The idea here is to break the problem into smaller, overlapping subproblems. We define a DP table where dp, I, j, represents the maximum dot product achievable using the first I elements of nums1 and the first j elements of nums2. At each step, we have 4 choices: include the current pair of elements in the dot product, skip the current element from nums1, skip the current element from nums2, or start a new subsequence. These choices allow us to recursively define our DP transition equation. The dynamic programming approach relies on well-defined base cases. For example, if one of the arrays is empty, it is impossible to form a valid subsequence, so the dot product defaults to negative infinity. This ensures the solution adheres to the problem constraints. We choose this approach because it avoids the exponential growth of subsequences by focusing only on overlapping subproblems, which we solve using memoization. The time complexity of this method is O and *m, where n and m are the sizes of the two arrays efficient enough to handle the problem's constraints. Other strategies, such as greedy methods, fail to account for scenarios where the optimal solution requires skipping elements in both arrays. For instance, blindly selecting the largest pairwise product at each step might miss opportunities to achieve a higher overall dot product. The dynamic programming approach, on the other hand, guarantees correctness by systematically exploring all possibilities. The key insight is that the dot product must include at least one pair of elements, and the DP equation naturally handles cases where elements are skipped or new subsequences are started. In terms of space complexity, the DP table requires O and *m space because we store results for all combinations of the first I elements of nums1 and the first j elements of nums2. While this is efficient, we can optimize further using a rolling array, reducing space complexity to O, min, n, m. However, this comes at the cost of added implementation complexity. The time complexity remains O and *m, which is optimal since we must consider every pair of elements at least once. Alternatives to this approach, such as brute force or greedy methods, either fail to meet the problem's constraints or cannot guarantee correctness. Dynamic programming strikes the right balance, combining theoretical efficiency with practical feasibility. By focusing on recursion and memoization, this strategy ensures that we systematically explore all possibilities without redundant computations, making it both robust and efficient for this problem. In this problem, we're tasked with finding the maximum dot product between two subsequences derived from two integer arrays, nums1 and nums2. A subsequence, as you might recall, is formed by removing some or none of the elements from an array while maintaining the relative order of the remaining elements. The challenge is to compute this maximum efficiently, as the brute force approach of trying all possible subsequences would be computationally expensive. To solve this, we use dynamic programming. The key idea is to define a state, dp, I, j, which represents the maximum dot product of two subsequences where one ends at index I in nums1 and the other at index j in nums2. This allows us to break the problem into subproblems. For the base case, if either I or j equals 0, the subsequences involved are either empty or consist of a single element, so the dot product is simply nums1, I, times nums2, j. This sets the foundation for building the solution iteratively. To compute the value of dp, I, j, we have three main options. First, we can include both current elements, nums1, I, and nums2, j, in the subsequences. In this case, we add their product to the best dot product up to dp, I1, j1. Second, we can exclude the current element from nums1, which means the value of dp, I, j, is derived from dp, I1, j. Third, we can exclude the current element from nums2, taking the value from dp, I, j1. Additionally, we consider the product of nums1, I, and nums2, j, by itself, representing the case where only these two elements are used. Combining these, the transition formula becomes the maximum of these options, nums1, I, *nums2, j, plus dp, I1, j1, if valid, dp, I1, j, dp, I, j1, and the product alone. To implement this efficiently, we construct a 2D DP table with dimensions equal to the lengths of nums1 and nums2. We initialize the table with negative infinity to handle the possibility of negative dot products, and then fill it iteratively, row by row and column by column, using the transition equation. Once the DP table is filled, the maximum value within it represents the solution to our problem, as it reflects the highest dot product achievable between any two subsequences. One critical insight is how the algorithm handles negative values. Both nums1 and nums2 can contain negative numbers, which means dot products can also be negative. By initializing the DP table with negative infinity, we ensure that we correctly track the true maximum throughout. Now, there are also edge cases to consider. For instance, if nums1 and nums2 each contain only one element, the solution is simply their product. If both arrays consist of all negative numbers, the result is the product of the two least negative numbers, as they are closest to 0. When zeros are present, they are ignored unless their inclusion maximizes the dot product. This dynamic programming approach excels because it inherently explores all possible subsequences without explicitly generating them, making it vastly more efficient than brute force. The DP table serves as the core data structure, enabling efficient computation and state transitions. Analyzing the complexity of the algorithm, the time complexity is O, n*m, where n and m are the lengths of nums1 and nums2. This is because we iterate through all pairs of indices I and j to fill the DP table. The space complexity is also O, n*m, due to the size of the DP table. However, we can optimize the space usage to O, min, n, m by storing only the current and previous rows or columns. Additionally, further optimizations such as early pruning can be applied. For instance, if the product nums1 I nums2 j is smaller than the current maximum, further computation for that pair can be skipped. To implement the algorithm, we initialize the DP table with negative infinity, then iterate through each pair of indices, computing the maximum dot product for each state using the transition formula. This approach balances efficiency and clarity, allowing us to handle the problem's constraints effectively. Finally, once the DP table is fully constructed, extracting the result is straightforward. We simply find the maximum value across all rows in the table, as this represents the highest dot product achievable between any two subsequences of nums1 and nums2. The result is then returned as the solution. This completes the algorithm, which combines dynamic programming, careful handling of edge cases, and potential optimizations to provide an efficient and robust solution to the problem. The provided code solves the problem of finding the maximum dot product of two subsequences using dynamic programming. Here's a detailed explanation of the solution. 1. Initialization. The max.product function takes two integer lists, nums1 and nums2, as input. The dimensions of the dynamic programming table DP are determined by the lengths of nums1 and nums2. DP, I, j, represents the maximum dot product of subsequences formed from the first I elements of nums1 and the first j elements of nums2. The table is initialized with negative infinity, float, I and f, to handle cases where no subsequence is valid. 2. Dynamic programming transition. A nested loop iterates through each combination of I and j, representing the indices of nums1 and nums2 respectively. The dot product of the current elements nums1, I1, and nums2, j1, is calculated. The DP, I, j, value is updated by considering the following options. Skip the current element in nums1, value comes from DP, I1, j. Skip the current element in nums2, value comes from DP, I, j1. Include the current pair in the dot product, value comes from DP, I1, j1, plus dot product. Start a new subsequence with the current pair, value is simply dot product. 3. Result. After the loop's complete, the value DP, n, m, contains the maximum dot product of any subsequences derived from nums1 and nums2. This approach ensures all edge cases are handled, including scenarios where one or both arrays contain negative values, and cases where subsequences of different lengths are chosen. The time complexity is O, n*m, where n and m are the lengths of the input arrays, making the solution efficient for large inputs. Here, we are implementing the solution to find the maximum dot product of two subsequences in Java. First, we import the necessary utilities and define the solution class with the method max.product. Inside this method, we take two integer arrays, nums1 and nums2, and determine their lengths, n and m, respectively. Next, we initialize a 2D DP array to store intermediate results, setting all its values to a very small number, integer.man_value, to handle cases where subsequences could have negative products. This ensures we don't unintentionally consider uninitialized values. After initializing the DP array, we iterate over each element of nums1 and nums2 using nested for loops. Within these loops, we calculate the dot product of the current pair of elements from the two arrays, which is nums1, I1, multiplied by nums2, j1. This value is then used to update the DP array by considering multiple cases. Specifically, we use math.max to evaluate the best possible value for DP, I, j, by either skipping the current element from nums1, skipping the current element from nums2, or including the current pair in the subsequence. Finally, we also consider starting a new subsequence with the current dot product value. The logic for updating dp, I, j continues here, where we use nested math.max calls to ensure that each case is thoroughly evaluated. This involves comparing the maximum value obtained when skipping elements or including the current pair, as well as the scenario where a new subsequence begins. After all iterations are complete, the dp array will contain the maximum dot product for every combination of subsequences at various lengths. The result of the overall computation is stored in dp n m, which represents the maximum dot product when using all elements from nums1 and nums2. Finally, we return dp n m as the output of the method, completing the implementation. This dynamic programming approach ensures that we efficiently compute the result by breaking the problem into smaller subproblems and building up the solution step by step. To solve the problem of finding the maximum dot product of two subsequences, we start by setting up the initial parameters. Here, we have nums1 as 2, 1, minus 2, and nums2 as 3, minus 6, 1. The lengths of these arrays are 3 each, so n and m are both equal to 3. We'll use a dynamic programming table, dp, to store the intermediate results. This table is initialized as a 4x4 matrix filled with I and f, which represents the smallest possible value. The extra row and column allow us to handle base cases where one of the subsequences is empty. Now, we start iterating through the elements of both arrays, calculating the dot product for every pair and updating the dp table accordingly. In the first iteration, at I equals 1 and j equals 1, we consider the pair nums1, 0, and nums2, 0, that's 2 and 3 respectively. Their dot product is 6. This value is used to update dp, 1, 1, using the formula that considers 4 options: the current value of dp, 1, 1, the value above it in the table, the value to its left, and the value obtained from starting a new subsequence using the current pair. The maximum of these options is stored in dp, 1, 1. Here, we compute the maximum value for dp, 1, 1, as 6, and the updated dp table reflects this change. Moving to I equals 1 and j equals 2, we now consider the pair nums1, 0, equals 2 and nums2, 1, equals dash 6. Their dot product is 2 asterisk dash 6 equals dash 12. To update dp, 1, 2, we again calculate the maximum of 4 options: the value in the previous column for the same row, the value in the previous row for the same column, the sum of the current dot product and the value from the previous diagonal cell, and the dot product itself if we start a new subsequence. Here, the maximum value remains 6, so dp, 1, 2, is updated to 6. The table now shows that the maximum dot product achievable so far remains 6, even as we include this new pair. This demonstrates how the dynamic programming approach ensures that we always keep track of the best subsequence options up to this point. Next, for I equals 1 and j equals 3, we look at the pair nums1, 0, equals 2 and nums2, 2, equals 1. Their dot product is 2 asterisk 1 equals 2. Again, we use our formula to update dp, 1, 3, which is the maximum of the previous values in the row, the column, the diagonal plus the dot product, and the current dot product itself. The maximum value here remains 6, so dp, 1, 3, is updated to 6. Now, moving to I equals 2 and j equals 1, we shift focus to the pair nums1, 1, equals 1 and nums2, 0, equals 3. Their dot product is 1 asterisk 3 equals 3. To update dp, 2, 1, we again consider the maximum of the 4 possibilities, which include the value directly above, the value to the left, the diagonal value plus the dot product, and the dot product itself. The highest value remains 6, so dp, 2, 1, gets updated to 6. At this stage, the table demonstrates how we are systematically building up the solution by comparing all possible subsequences. Following the same process for the remaining cells, we complete the dp table. The final matrix looks like this: all valid cells in the table contain the value 6, which is the maximum dot product achievable for this example. The result is found in the bottom right cell, dp, 3, 3, which is 6. This means the maximum dot product of any two non-empty subsequences from nums1 and nums2 is 6. For a better understanding, we can apply the same algorithm to another example. Consider nums1 equals, -1, -2, -3, and nums2 equals -4, -5, -6. Even with all negative numbers, the method still works. We can choose subsequences like -1 from nums1 and -4 from nums2, which gives a dot product of 4. By following the same dynamic programming approach and carefully updating the DP table, we find the maximum dot product for this case is 4. From these examples, we can make some key observations. First, it's important to always consider starting a new subsequence using the current pair's dot product. This ensures that we capture the best possible result, even if previous subsequences yielded smaller values. Second, unlike other subsequence problems where empty subsequences might be allowed, this problem requires non-empty subsequences, which is why we initialize the DP table with INF. Even negative numbers can provide a valid solution, as shown in the second example. For instance, if nums1 equals 1 and nums2 equals -1, the dot product is simply 1 * -1 equals -1, which is the correct output. By carefully handling these edge cases and leveraging the dynamic programming approach, we can solve the problem systematically and efficiently. To understand the time complexity of our solution, we start by analyzing the nested loops. The outer loop iterates over each of the n elements in nums1. For every iteration of this outer loop, the inner loop runs through all m elements in nums2. Inside this inner loop, the operations performed include calculating the dot product of two elements, which is a constant time operation, and evaluating the maximum of 4 values using the max function, which is also constant time. Since both loops are nested, the total time complexity is derived by multiplying the number of iterations of the outer and inner loops. This results in O(n) for the outer loop times O(m) for the inner loop, and since each iteration involves O(1) work, the overall time complexity becomes O(n*(m). Now let's look at the space complexity. The primary contributor to the space usage in this solution is the DP table, which is a 2D array of size, n+1 is x, m+1. Here, n is the length of nums1 and m is the length of nums2. Each cell in the table holds an integer value, so the memory required to store the table is proportional to the product of n+1 and m+1. Additionally, there are a few auxiliary variables such as the loop counters and intermediate storage for calculations like dot_product, but these require only constant space, or O(1). Therefore, the overall space complexity is dominated by the DP table, and we can express it as O(n*(m). When comparing this dynamic programming approach to a brute force solution, the efficiency of our method becomes even clearer. A brute force approach would involve generating all possible subsequences of nums1 and nums2. For an array of length n, the total number of subsequences is 2(n). This means that for both arrays, we would have 2(n*(2)m pairs of subsequences to evaluate, or 2(n plus m) in total. For each pair, we would calculate the dot product, which in the worst case would require O, min, n, m operations. As a result, the time complexity of the brute force approach becomes O, 2(n plus m, min, n, m, which is prohibitively expensive for large inputs. In contrast, our dynamic programming solution avoids this exponential growth and computes the result in polynomial time. Finally, let's analyze the best, average, and worst cases for our algorithm. Regardless of the input, the complexity remains O(n*(m), because the algorithm always needs to compute all n*(m) entries in the DP table. This is true for the best case, the average case, and the worst case scenarios. Mathematically, the complexity is determined by the nested loops. The outer loop runs 4n iterations and the inner loop 4m iterations, resulting in n*(m) iterations in total. Since each iteration performs a constant amount of work, the time complexity is O(n*(m). Similarly, the space complexity remains O(n*(m) due to the size of the DP table. This consistent behavior makes the algorithm predictable and efficient, even for larger inputs. When working on this problem, there are some common pitfalls to watch out for. One major mistake is not properly accounting for negative numbers in the input. Negative values can significantly affect the outcome of the dot product, and sometimes including a negative number in the subsequence actually leads to a higher result. It's crucial to ensure your algorithm handles these cases correctly. Another frequent issue is misunderstanding the concept of a subsequence. Remember, a subsequence does not have to be contiguous, the elements can be selected as long as their relative order is preserved. This is different from subarrays, which are always contiguous. Additionally, attempting a brute force solution by generating all possible subsequences for both arrays is impractical for larger inputs. This approach has exponential time complexity, which is not feasible. Lastly, when using dynamic programming, it's important to keep the state definition simple. For example, using a dp(i)j table where each entry represents the maximum dot product achievable with the first I elements of nums1 and the first j elements of nums2 keeps the problem manageable and avoids unnecessary complexity. Next, let's talk about edge cases and some valuable insights for interviews. A common oversight is neglecting to test edge cases. Scenarios like arrays composed entirely of negative numbers, arrays of unequal lengths, or arrays with 0 elements can reveal bugs in your solution. It's always a good idea to validate against a wide range of test cases. From an interview perspective, one key insight is that this problem revolves around maximizing the dot product, so exploring both greedy and dynamic programming approaches can be helpful. Pay close attention to how subsequences are defined, as this is central to solving the problem correctly. The pattern here is similar to other dynamic programming problems involving subsequences, like longest common subsequence or maximum sum increasing subsequence. Recognizing this connection can help you structure your solution effectively. While brute force might initially seem intuitive, it is computationally expensive, making dynamic programming a far more efficient approach. Interviewers may also ask about optimizing space complexity. For instance, if only the last row or column of the DP table is needed at any step, consider reducing the table to a 1D array to save space. Lastly, let's explore some related problems and alternative approaches. This problem shares similarities with other dynamic programming challenges. For example, LeetCode 72, edit distance, and LeetCode 1143, longest common subsequence, also involve operations on two sequences. Similarly, problems like LeetCode 53, maximum subarray, and LeetCode 1035, uncrossed lines, highlight specific techniques for subsequences and optimization. Understanding these problems can provide additional perspectives and strategies. As for alternative approaches, a greedy solution might work for simpler cases by selecting elements that maximize the dot product at each step. However, this approach often fails in edge cases where decisions at earlier steps limit future options. Dynamic programming remains the most robust approach, where you define a 2D table, dp(i)j, to store the maximum dot product for given prefixes of the arrays. This method is efficient, with a time complexity of O and *m, but it requires careful implementation to avoid bugs. Another possible approach is divide and conquer, which breaks the problem into smaller subproblems. While theoretically interesting, it's usually less efficient and more complex than dynamic programming for this specific problem. Great job making it to the end. To summarize, we explored the max dot product of two subsequences problem, broke it down into a dynamic programming solution, and analyzed its complexities. Remember the key insights for tackling similar problems in the future. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!